walk here 3 steps and walk there 2 steps, or do it the other way around and still you reach the same position. But that means that these two motions commute, right? But on the other hand, if I say that take a left turn and walk 2 steps, I'll be there. But walk 2 steps and take a left turn, I'll be there. Huh? That doesn't commute. So those kind of things. So these are the same kind of operators. Or if you want to think in terms of those vectors, that the first one does not change. It's only if you have an eigenfunction, then the only thing that an operator is doing, an eigenfunction of that operator, then the only thing that it's doing is to increase or decrease the length of the vector. Whatever the eigenvalue is, it's a constant number multiplied by the function. Okay. So let me see if I have to tell you something else before I can start on this particle in a one-dimensional box. Assuming that you all know about probability, discrete probability and continuous probability, mean, average, first moment, second moment, variance. Okay, in that case, whenever we need it, we will come back to it, but it's there in the second set of notes for quantum. You can also read it. We'll just skip it for the moment. When we maybe another lecture from now, when we need it, I'll introduce that. Okay, because what I wish to do first, in fact I should do it later, because then I have to link quantum mechanics to probability as well. Okay, so in that case what I'll do is to start with the most easiest example in quantum, and that is what we call particle in a one-dimensional box. What's this one-dimensional box? It means that think of a straight line and the particle is allowed to just move on this line, not above this line, not perpendicular, just on the line. Okay, and how do you ensure that the particle stays fixed on this line? So, okay, our dimension is only 1, okay, and so the particle is moving, and if you want to see any quantized behavior, which you saw yesterday for the motion of this string, when did the quantization creep in? When I solved it, it was not quantized. Boundary conditions. So which means that these ends of the strings were fixed. Quantization always comes when you have some confinement. Okay, in each and every case, wherever you see. So I'll take this one-dimensional box. That's my box. Now, if you're laughing about it, then wait till you go on to multi-dimensional spaces. I think I already saw those E1, E2, E3 and so on in your maths lecture. So that's a one-dimensional box. What's there to laugh about, huh? Well, all of you are now accustomed to think in multi-dimensional spaces? Huh? Not yet? Okay, I'll add more to the confusion in that case. So what I do is I confine it, that's my x direction, between x is equal to 0 and x equals L. So the particle will stay only between 0 and L. How do I do that? I ensure that by putting a potential of 0 between these boundary conditions, and outside I put infinite potential. So it's an infinitely high wall, the particle cannot jump out. So the arrows just mean that it's going all the way to infinity. Okay, there is no physical boundary like this, okay? Absolutely, there is no physical boundary, no vertical physical boundary. It's only separating these two regions. The potential inside is 0, between 0 to L on this line only. Okay, outside this line, the potential is infinite. So the particle can move only between 0 and L, not above this, okay? So, because of this graphical picture, a lot of students tend to think that it's going above somewhere. No, it stays, the particle stays over here on the line. Now, I would like to see how this quantization results in the change of energy. If the particle was free, then it could take on any energy, right? Now that it's quantized, I'll go back to the Schrodinger equation and try to solve that. So minus h cross square by 2m. So let's call this region 1, region 2 and region 3. D square psi in region 1 by dx square plus infinite times psi, the potential is infinite, is equal to E of psi. What value? I could even take this on the other side, huh? E minus infinite of psi. What value of psi would satisfy this psi 1, huh? That's the only possibility, right? Well, even without doing the maths, I can tell you that since outside it's infinite, the potential is infinite, my particle will not be there. Which means my wave function which describes my particle should be 0. So likewise, so this gives me psi 1 is equal to 0 is also equal to psi 3. It's the same case. So the wave does not exist outside the box. Inside the box, let's see what the situation is. D square psi of 2 dx square plus potential is 0 is equal to E of psi 2. Let me rearrange this a bit. D square psi by dx square plus 2m E by h cross square psi is equal to 0. Rings any bell? Huh? Have you seen that equation before? Huh? When? Yesterday. Great. Instead of this 2me, what we had was k square. K square, huh? Small k square. So I will define k square is equal to 2m E by h cross square. You know the solutions of this. You know the solutions were psi is equal to a cos kx plus b sin kx. And in fact, the boundary conditions are also the same. I've used the same variables here also. So the two boundary conditions that you have are psi at 0 is equal to 0 and psi at L is equal to 0. So I mean, what it gives me again, let's not solve it. So psi, let me try to remember, was b sin kx is equal, kl is equal to n pi. So n pi by L times x. From yesterday. Okay. Uh, the condition that came out was K L is equal to N pi. Let me square that. K square L square is equal to N square pi square, and put back the value of K, which was K square, sorry, 2me by h cross square. L square is equal to N square pi square. Yeah? Some very important discussions going out there within the zebra shirt. Huh? Something very important. You know, you are in the zebra shirt. Yeah. Yeah. Something really important, then tell me. No? Then let me allow me to finish. Huh? So what you get out of that